Morning to all of you, and I would like to welcome you all to this presentation today, which is on application of stochastic limit analysis to geotechnical stability problems. So this is the outline of today's presentation, and in the introduction I will talk about the importance and the objectives of the present research work, and then the theory and literature review related to the present work will be discussed. And after that, I will present two studies which I have investigated up to now. One is the deterministic study, boundary effects, and the second is the probabilistic study, which is about risk assessment of landslides. And in the last part of the presentation, the future research objectives will be discussed. So coming to the types of uncertainty, uncertainty in geotechnical engineering can be classified into two types. One is aleatory, and the second is epistemic. So aleatory uncertainty is something which is inherent and it cannot be reduced or eliminated. Example, spatial variability of soil properties in a nominally uniform soil layer. Whereas epistemic uncertainty is something that can be reduced or even eliminated. So in the present research work, I have just focused on the aleatory uncertainty that is due to spatial variability of soil properties. Now, most of the stability analysis in geotechnical engineering, they adopt a deterministic approach, and in it the uniform soil properties are considered and the spatial variability is assumed to be considered indirectly by considering a factor of safety. Now obviously there are some limitations in this regard because deterministic analysis does not explicitly account for spatial variability. And what happens is, if the factor of safety using a deterministic approach, which ignores the spatial variability, is less than the true factor of safety of the slope, the design will be uneconomical. And on the other hand, if it is greater than the true factor of safety of the slope, the design will be unsafe. So therefore, we need to systematically quantify and implement the uncertainty into analysis in order to achieve reliable designs. Now coming to the importance of the present study, slope stability is an area that is highly amenable to probabilistic treatment, and it continues to receive much attention, and this could be because landslides have severe consequences. A recent study revealed that between 2004 and 2010, more than 30,000 people have been killed due to landslides, and these landslides exclude those caused by earthquake. Apart from death causing fatalities, landslides also cause damages to infrastructure and properties worth billions of dollars every year. Though many factors are responsible for causing landslides, rainfall is found to be the most common cause. And this figure, it shows an example of a rainfall-induced landslide, which happened in Colombia in 2010, and 60,000 meter cube of soil was displaced and 20 people were killed. Due to spatial variability of soil properties, complex failure mechanisms also tend to evolve during landslides, and therefore there is a need to develop innovative methods for landslide risk assessment which can consider the uncertainty in the soil properties. So now I will discuss the objectives of the present study. One of the major objectives is to combine random field and finite element limit analysis. Why? Because finite element limit analysis is an excellent tool for predicting the collapse state of the slopes, whereas random field can effectively consider spatial variability. And the second stage involves incorporating unsaturated seepage analysis, so that the framework of random field and finite element limit analysis can then be used to predict the probability of failure during rainfall. And lastly, using the quantitative risk assessment of landslides framework, the risk from different sources of uncertainty can be evaluated. Now this method is general in nature, and it can be extendable to, and it is extendable to other geotechnical engineering problems as well. But to begin with, we actually did a 1D deterministic study, and then we progressed to a 1D probabilistic study. And this 1D deterministic and probabilistic study involve unsaturated seepage analysis, and our ultimate goal is to perform 2D probabilistic studies which also involve unsaturated seepage analysis. So now I'll discuss few of the commonly adopted probabilistic approaches for slope stability. The first or the second moment method, it yields a reliability index beta, and here the mu fs is the factor of safety based on the mean values, and sigma fs is the standard deviation in the factor of safety. And the problem with FOSM is that it yields non-unique solutions depending on how the problem is formulated. Then we have the first order reliability method, which yields another reliability index, which is called as Hazoff-Allende reliability index. And this process, it basically involves finding a set of random variables x having a mean mu and standard deviation sigma, so that the limit state function g is minimized. And over here CR is the correlation between the random variables. Now form is a better procedure than FOSM, but the problem is of determining the limit state function in case of complex problems. And then we have the Monte Carlo simulation technique, in which multiple simulations are performed based on different values of random variable which are sampled from a distribution, and it yields the probability of failure, which is defined as the number of simulations resulting in slope failure divided by the total number of simulations. And Monte Carlo simulation, it is simple in concept and it can be extended to difficult problems, but sometimes large number of simulations may be required when the probability of failure is low, and therefore in those cases we can use different sampling methods to reduce the number of simulations. Coming to the random field theory, what is a random field? A random field is, in a random field, the soil property at a point, it is assumed to be a random variable, and it is then considered to be correlated to the random variables at adjacent points in some manner. And the set of all random variables in a domain is called a random field. Three quantities are actually required to characterize a random field: the mean, variance, and the spatial correlation length. Now if you have a look at this figure shows two random fields having the same mean, variance, but different spatial correlation length. We can have an idea about the spatial correlation length. So spatial correlation length, basically it defines how the field varies in the space. So if the spatial correlation length is small, the field will vary rapidly, and if it is large, the field will vary gradually. Though the first order methods, FOSM and form, have been combined with random field for slope reliability, there are some limitations in this regard, and it is basically due to the use of limit equilibrium methods. Now limit equilibrium methods, they cannot properly consider spatial variability. On the other hand, we have the random finite element method, which basically combines a random field and finite element together for predicting the slope reliability, and it can effectively consider the spatial variability. And regarding the combination of random field and finite element limit analysis, not many studies are present in the literature, so there is much scope of work in this area. Now for probabilistic slope stability analysis, we require a deterministic method of assessing the stability of slope. So here I will discuss some of them. Limit equilibrium method is the most simple one, and it has been used for quite a long time, but its biggest disadvantage is that it requires an assumption regarding the failure surface, and poor assumptions of the failure surface can lead to poor estimates of the stability. Finite element method, on the other hand, it does not require any assumption about the failure surface, but it requires excessively large computational time, and FEM basically relies on non-convergence as an indicator of collapse in the slope. So care should be taken that the non-convergence is due to collapse only and not due to some other numerical effect. A common limitation that can be observed in these two methods is that there is no indication about the error. Finite element limit analysis, on the other hand, it has no assumptions regarding the failure surface. It is efficient, it is robust, and it gives an it gives a bound on the error. So this figure, it shows an example of limit equilibrium method combined with random field. This shows an example of finite element method combined with random field, and this shows an example of finite element limit analysis combined with random field. And we can see how well the finite element limit analysis can predict the collapse state in slopes. Now, since I have performed few studies on rainfall induced landslides, I would like to present the two most important factors which affect the stability of a slope during landslides. The first is the saturated hydraulic conductivity. Now, previous researchers have suggested that instead of using saturated hydraulic conductivity alone, it is better to use the I by Ks ratio, where I is the rainfall intensity and Ks is the saturated hydraulic conductivity. And if you have a look at this figure, we can see that as the I by Ks ratio increases, there is a greater reduction in the pore water pressure. So previous studies reveal that a critical I by Ks ratio exists at which, beyond which there is a maximum reduction in the pore water pressure and the factor of safety. And the second important factor is the rainfall characteristics. Now, previous studies reveal that a critical return period and a duration exists at which the factor of safety is minimum. And also 4 rainfall patterns have been investigated, among which the advanced rainfall pattern has been found to be the most critical in reducing the pore water pressure and the factor of safety of the slope. Now we'll talk about the risk assessment framework. So this figure shows the traditional risk assessment framework, where the probability of failure is calculated from a number of Monte Carlo simulations and it is multiplied by a fixed consequence to get the risk. On the other hand, we have the new framework for risk assessment, which says that the consequence should be assessed individually for each failure, and this leads to a modified definition of risk, as can be seen. So I will be adopting the new quantitative risk assessment framework in my studies. Now, coming to the studies on soil spatial variability, studies which investigated the influence of shear strength variability on slope reliability. Now, most of the studies which investigated the influence of shear strength variability on slope reliability, they considered the influence only on the probability of failure. Wang et al. They investigated the influence of shear strength variability on landslide risk, but the results had a significant gap, and it was basically due to a coarse uniform mesh which was used for assessing the stability of slope. And then studies which investigated the influence of spatial variability on in saturated hydraulic conductivity on slope reliability. First of all, there are a few studies in this area, and also most of the studies, they investigated the influence once again only on the probability of failure. And lastly, we have the rainfall characteristics. So probably most of the studies which investigated the influence of which investigated the rainfall induced landslide using a probabilistic approach, they considered a uniform rainfall and no variation was generally observed, and therefore there is a scope for evaluating the influence of rainfall pattern with spatially variable saturated hydraulic conductivity on the landslide risk. Now, as I mentioned before, as the first step towards the big research plan, we initially did a deterministic study, and this is the deterministic study that I will present now. So most of the most of the studies which considered rainfall-induced landslides, they generally have an infinite slope with an impermeable boundary. So this sort of predetermines the failure surface. And in reality, it is possible that other boundary conditions can exist. So no study has actually systematically investigated the influence of different boundary conditions on the failure. So that is why the objectives of the present study are to evaluate the effects of boundary conditions on the failure depth when we have different rainfall intensities, we have different slope inclinations and different soil cohesion. So coming to the methodology, I considered an infinite slope, and this figure on the right, it shows the geometry of the slope. I will explain the geometry later. And rainfall infiltration was modeled using 1D seepage analysis, which was done in Hydrus 1D. Now Hydrus 1D basically solves a modified form of 1D Richards equation, and we use the Van Gunnington model for the Van Gunnington model as the hydraulic model. Slope stability was assessed using this analytical expression, where phi dash and c dash, they are the effective shear strength parameters, and alpha is the slope inclination, SE is the effective degree of saturation, UW is the pore water pressure at the failure depth, and W is the weight of the failing soil mass. Now I use the Mohr-Coulomb model to define the shear strength in terms of effective stress parameters, and the Bishop's formulation was used to extend the Mohr-Coulomb model to unsaturated soils. And in Bishop's formulation, the pore air pressure UA was considered as 0, and the coefficient of effective stress Chi was considered equal to the degree of saturation SE. Now coming to the geometry of the model that I considered, the slope has an inclination alpha, and it basically considers a 1 meter thick soil layer lying above a rock, and the water table is measured 2 meters along the Z direction, which is basically the slope normal direction, and the initial conditions are hydrostatic. The rainfall intensity is I, and the flux infiltrating the slope is Q, and is assumed to infiltrate normal to the slope. And the failure depth dF is measured along Z, that is in the slope normal direction. So we considered different boundary conditions through adopting different ratios of Ks1 by Ks2. So Ks1, as I showed in the previous figure, is the saturated hydraulic conductivity of the soil, and Ks2 is the hydraulic conductivity of the rock, and this index was basically used as an index of degree of permeability of the boundary. So if this ratio is very small, the boundary is fully drained, it allows the flux to drain out, and if it is very large, it implies an impermeable boundary, and all the infiltrated flux is accumulated at the boundary. So we considered 4 cases. Case 1 considers alpha equal to 36 and a cohesionless soil, C dash equals to 0, and this was the base example. In case 2, we increase the cohesion. In case 3, we change the slope inclination to 40 degrees, but the cohesion was the same. And in case 4, both the slope inclination and the cohesions were changed. Now all the boundary conditions which I have shown in table 1 were adopted for all these 4 cases, and the rainfall intensity was considered in terms of the I by Ks1 ratio, where I is the rainfall intensity and Ks1 is the saturated hydraulic conductivity of the soil. And we considered this rainfall to vary in this range, and we considered 24 different rainfall intensities. Now coming to the results, this figure shows the profiles of the pore water pressure and the factor of safety at rainfall intensity of 0.01, and here we can see that the wetting front, it reaches the boundary, and therefore the failure will depend on the boundary, so whether the flux is allowed to drain away or the flux is accumulated at the boundary. And now in this case we have the failure occurring only for the impermeable boundary. I have just shown only 3 boundary conditions to clearly illustrate the process. And then if we increase the rainfall intensity, the failures can occur during the propagation of wetting front, and in this case the failure will then be completely independent of the boundary condition. Now in this figure, the failure occurs for all the 3 boundary conditions which are shown. This figure shows the variation in failure depths dF with the boundary conditions. So this over here is a fully drained boundary, and this over here is an impermeable boundary. So I have shown only 4 rainfall intensities. So when the rainfall intensity is below 0.4, we can see the boundary effects. The dashed line shows those failures where boundary effects could be observed. and when the rainfall intensity exceeds this value, there is no effect of boundary on the failure. A critical I by KS1 ratio is observed, which demarcates this boundary influence. Now in case 1, all the failures were due to loss of suction. In case 2, we see that there is no influence of rainfall intensity on the failure depth, and all the failures have a constant depth, and this is because the failures occur due to generation of positive forward pressure. Now this figure shows the variation in failure depth dF with the rainfall intensity for all the 4 cases. The results have been plotted in this figure only for an impermeable boundary. So if you have a look at the critical rainfall intensities, it is 0.4 for case 1, and it is 0.0625 for case 3, and it is 0.3 for case 4. Now this critical intensity basically is the value of rainfall intensity up to which the boundaries exercise influence on the failure depths. So once this rainfall intensity is exceeded, the boundaries have no influence on the failure depth. And from this figure, we can judge that by looking for case 1 and case 3, that when we increase the slope inclination, the boundary will have less influence. And if we compare case 3 with case 4, we can see that the increase in soil cohesion, it causes an increase in the boundary influence. So now coming to the conclusions, we investigated the influence of boundary conditions, and it is observed that the failures for a permeable boundary will only be shallow, and if the boundary is less permeable, the failure could be deep or shallow depending on the rainfall intensity. And when failure occurs due to loss of suction, a critical I by KS1 is observed up to which the boundaries exercise influence. And when failures occur due to generation of positive forward pressure, the rainfall intensity has no influence. When soil cohesion is increased, the critical I by KS1 is increased, which means an increase in the boundary influence. And when slope inclination is increased, the critical I by KS1 decreases, which implies a decrease in the boundary influence. So now I'll explain the 1D probabilistic study. And now rainfall-induced landslides, basically they occur in initially unsaturated soil slopes where the negative forward pressure, it contributes to the soil strength and slope stability. And in the event of a landslide, there are 2 things which can determine risk. One is the saturated hydraulic conductivity, because it controls the infiltration process, thereby affecting the forward pressure distribution and ultimately affecting the shear strength and the slope stability. And the failure mechanism, because they affect the failure depths as we observed in the previous 1D deterministic study. So the objective of the present study is to investigate the influence of spatial variability in the hydraulic conductivity on the probability of failure, consequence and risk, and also determine the influence of different failure mechanisms on risk. Now the same methodology as was adopted in the deterministic study was considered for this case as well, and I considered 2 examples having different soil cohesions. Now these 2 examples were considered to create different failure mechanism, and if we have a look at this figure, we can see that all the failures at all depths in example 1 are due to loss of suction only, and failures in example 2 in the top half, they are due to generation of positive forward pressure. So now coming to the random field study, the saturated hydraulic conductivity was considered as a log normal stationary random field having a mean 8.64 meters per day and coefficient of variation equal to 1. I consider the uniform rainfall intensity equals to 0.25 times the mean value of Ks. To consider the different degrees of spatial variability, 8 spatial correlation lengths were considered, and I performed 2000 Monte Carlo simulations for each spatial correlation length. Now this figure shows the results of the probability of failure, consequence and risk for example 1. And we can see that the probability of failure, it decreases with an increase in spatial correlation length, whereas the consequence increases with increase in spatial correlation length. And also the risk is maximum when the spatial correlation length is equal to 1. Now if we compare this with example 2, now in this figure the dashed lines are for example 2, and we can see that the probability of failure and the consequence, they both vary in a similar manner as in example 1, but the variation occurs over a different range of values. So in case 2, the probability of failure varies over a lower range and the consequence varies over a higher range. And in case 2, the risk is maximum when spatial correlation length is 0.5, and another noticeable thing is a decrease in the risk, an increase in the risk for small spatial correlation length. Now this figure, it shows the failure mechanisms occurring, and in this figure the blue hollow points, they show failure due to loss of suction, and the red solid points show failure due to generation of positive forward pressure. And the black solid line, it shows the analytically estimated forward pressure at failure. I have shown the results for 3 spatial correlation length for both the examples, and we can see that when the spatial correlation length is small, there is more uncertainty in the forward pressure at failure, and as the spatial correlation length increases, the forward pressure at failure, the trend becomes much more uniform and linear because the soil also becomes uniform. And this also confirms our assumption about the failure mechanism. We can see that most of the failures in example 1, they are indeed due to loss of suction, and in example 2, most of all the failures, in fact in the top half, they are due to generation of positive forward pressure. Now this figure, it compares the histogram from the histogram of failure depth from the 2 examples. But this is a very interesting figure. This number shows how many shallow failures are occurring, and this shows the number of deep failures. Now we can observe in general that when the spatial correlation length is small, there are more shallow failures and few deep failures. As the spatial correlation length increases, we can see that the shallow failures decrease and the deep failures increase, and this can be observed in both the examples. Another point that I want to make over here is the pattern of the distribution of failure depths. Now in example 1, most of the failures, they are concentrated near the surface, and in example 2, due to a change in the failure mechanism, the failure tends to be more deeper. So now this figure is basically, it explains the variation in probability of failure, why we have higher probability of failure at smaller correlation lengths, because we have more shallow failures, and why the consequence increases because the deep failure, they increase and the shallow failures decrease, and that is why we see an increase in the consequence. And another explanation is why was the consequence higher in example 2 compared to example 1, and we can see over here that most of the failures, they are concentrated near the middle of the soil profile. So failure in example 2 tends to be deeper compared to example 1, and this is the main reason for increase in consequence of example 2. Now coming to the conclusions, so we investigated the influence of spatial variability of Ks on the probability of failure, consequence and risk, and we saw that the probability of failure, it decreases with an increase in the spatial correlation length, the consequence increases with an increase in spatial correlation length, and the risk will be maximum at certain degree of spatial correlation length. And regarding the influence of failure mechanism, when failures occur due to generation of a positive forward pressure, the risk tends to be higher. So now, given the work that I have already done, I would like to outline the future work. So as an initial step, we just considered an infinite slope with 1D deterministic study, and then we did a probabilistic study to incorporate the random field and the risk assessment framework, and now we plan to extend this procedure to 2D slopes. by using finite element limit analysis as the deterministic method of slope stability. So what we are going to do is initially that we will consider the spatial variability in shear strength, and we will consider it for both drained and undrained slopes, and we will combine the random field and finite element limit analysis. And in finite element limit analysis we will use the adaptive meshing, and simultaneously the random field will be updated to account for the adaptive meshing. And then we plan to compare the risk that is obtained from both the adaptive and non-adaptive methods. In the second stage, we will investigate the influence of spatial variability of saturated hydraulic conductivity on the landslide risk. And what we are going to do is basically perform steady state seepage analysis using Hydrus 2D, and then we will import the pore pressures from Hydrus 2D into the finite element limit analysis codes and assess the stability, and then compare the risk for isotropic and anisotropic saturated hydraulic conductivity. And in the last stage, I will consider 4 rainfall patterns. These are the 4 rainfall patterns, so their influence on landslide risk needs to be investigated, and also consider the saturated hydraulic conductivity to vary spatially, and this will involve a transient seepage analysis, and this study will be done initially for an infinite slope and then extended to 2D slope. So this shows the future research plan. And there are different stages. I'll first be doing the infinite slope, and then do spatial variability due to shear strength, spatial variability due to hydraulic conductivity, initially for steady state, and then finally for transient seepage analysis. Alright, thank you.